On behalf of 24HourAnswers.com, I welcome you to today's lesson. In this video, we're going to look at intervals of concavity, and this cubic function hopefully looks familiar if you did watch the intervals of increasing and decreasing video where we looked at maximums and minimums. Now we want to talk about the concavity of this cubic function. In an earlier video, we did cover this exact same function, and we did determine the intervals of increasing and decreasing, and we even took it one step further and we applied the first derivative test to this same function. Now we're applying something new. We're going to talk about the second derivative and how it helps determine intervals of concavity. Up until this point, if you have not seen this video where we talk about concavity, a visual explanation, make sure you check that out. And if you're good to go with that, then we can go ahead and proceed with this. So, concavity, we want to find the second derivative, and if the second derivative is positive, then our function's concaving up. If our second derivative is negative, our function is concaving down. If you did check out the videos on the intervals of increasing and decreasing, we will take a very similar approach here. Let's go ahead and find the first derivative. This is the same derivative as earlier, so the derivative of 1/3 x cubed is going to be x squared. The derivative of 3x squared is a positive 6x, and the derivative of negative 16x is negative 16. Now we want to go one step further and find the second derivative, which is going to be the derivative of the first derivative. So therefore, the derivative of x squared is 2x. The derivative of 6x is 6. Now, very similar to our intervals of increasing and decreasing, let's set this second derivative equal to 0 and let's solve for x. This is going to give us our value of x at which our concavity may be changing, and that would be an inflection point. So solving for x, we have negative 6 equals 2x. Dividing by 2, we have negative 3 is equal to x. Now this is not our answer, but before we dive into the intervals, let's look at this graph again. Here's that same curve over in Desmos, and right around when x is negative 1, negative 2, negative 3. Right here is where we are going to have an inflection point. And the reason why I say we are going to have one, if you notice on the left side of negative 3, all these x values to the left of negative 3, this function is concave down. And then once we hit negative 3, this function starts to concave up. Concavity. Check out that visual explanation video for more on what concavity looks like. Now let's suppose we did not have that graph. Let's create a sign chart to test our second derivative on the left side of negative 3 and on the right side of negative 3. So here is that value that gave us a second derivative that's equal to 0. And just like in the intervals of increasing and decreasing videos, let's pick some test values. Anything to the left of negative 3, such as negative 4, and anything to the right of negative 3, such as 0. You could pick negative 2, negative 1, anything to the right of 0. Let's plug these test values into our second derivative, and all we care about is the sign of that second derivative. So the sign, when we take this test value of negative 4, when you plug it into here, you get 2 times negative 4 is negative 8. Plus 6, yes, that gives us a negative 2, but all I really care about is the sign. It is a negative sign. And then finally plugging in 0, 2 times 0 plus 6 gives us 6. All we care about is the sign of that second derivative. So thinking about our intervals now, over here to the far left, we have x values of negative infinity. Going over to the far right, we have x values of positive infinity. Now, based on these two little rules up here, when the second derivative is negative, our function's concaving down. When our second derivative is positive, greater than 0, like right here, our function is concaving up. Therefore, putting these things in interval notation, concave up, that's where our second derivative is positive. So anywhere from negative 3 to positive infinity, those values of x are where f of x is concaving up, and again, it's because our second derivative is positive. That statement right there. And then we are concaving down from x values of negative infinity all the way up to negative 3. And we can just double check this one more time over at the graph. We said we were concaving down to the left of negative 3 and concaving up to the right of negative 3. Now for bonus points, let's take this one step further and let's actually find that ordered pair. Let's actually find the location of that dot, both its x and its y value, and this is going to be called an inflection point because the concavity changes. That is what an inflection point is. To do that, the only thing we need to do is take the -3, plug it back into your original function to find the actual ordered pair of that inflection point. And our y value should be 66. So at -3, 66, that's going to be the ordered pair where our inflection point is. To verify that, over in Desmos, -3, 66, and notice that blue dot, that's the exact spot where we have our inflection point. And I hope you do see how we are concave down, and then right when we hit this spot, we start to concave up for this function f of x. And there you have it, an example of finding the intervals of concavity. We have a cubic function here. We have been talking about this cubic function for quite some time now in terms of maximums, minimums, intervals of increasing, intervals of decreasing, and now our intervals of concavity. And that's it for this video. I hope it helped. Be sure to check out our YouTube channel for more videos. Links to our social media are in the description below.